Thank you, Eike, and thank you everyone for being here. I know you all have busy schedules, and indeed, I'm very happy to be back again. I didn't know your fancy building that you have now, so you improved a lot. Okay, so today I'm going to talk about scaling provers in zero-knowledge SNARKs. This might look like a restricted, like a very specific topic, but in fact, scaling provers is the main problem probably that we have nowadays with zero-knowledge proofs. So for this talk, I will first give you some overview of what are SNARKs and how we build them. So like just a basic understanding. And then this will take a significant part of the talk because my goal is also to point you to the current research trends and what's interesting now. And then I will talk a bit of some results I've been working on recently. So first we go for this how to build SNARKs. So first, I'm sure all of you in this audience, you already know this, but what is a zero-knowledge proofs? So it's a process in which, I think this is in the middle. I don't know where to put it. Okay, in the middle of them. Okay, so it's a process in which a prover probabilistically convinces a verifier of the correctness of some statements, and the verifier learns nothing else. Okay, so a typical game example is we have an unsolved Sudoku, and Peggy wants to convince Victor that she knows a solution of this Sudoku, but of course doesn't want to tell the solution. There's always like a trivial protocol which consists on Peggy just giving the solution to Victor, but that's exactly what we don't want to do. We want to make sure Victor doesn't know anything. We're particularly interested in a specific type of zero-knowledge proofs, which are zero-knowledge SNARKs, and these are succinct, non-interactive arguments of knowledge. For this talk, let's think of a SNARK simply as anything that's sublinear on in the witness side. So again, a trivial solution could be that Peggy just sends the witness, or it could be maybe that she sends the encrypted witness or something like this if she doesn't want Victor to learn anything, but that's not the kind of things we want to have with us zero-knowledge SNARKs. We want to make sure that communication is of size less than the actual witness. Okay. So why are people so interested in SNARKs? As I can mention, there's quite some interest in SNARKs right now. And the reason is that SNARKs allow you to prove that computations are done correctly. So the situation is this: imagine we have a computer doing some computation, F, and this computer takes as input some, the input of the computation is some public information, and potentially also, but not necessarily, some private information, okay? And the goal of the server is to prove that this computation has been done correctly. For this, the server will not only compute the result of the computation, but also a small proof that this computation has been done correctly. Okay, so what we want is that somehow the size of the proof is less than the size of the computation. And the SNARKs, what they give you, and this is why they are so powerful, is because they give you short proofs of computational integrity. They allow you to prove that the computation is correct and verify this in a time that is much shorter than actually rerunning the computation and verify it has been done correctly. Again, the private input is optional. We are also interested in just verifying that computations are done correctly. Even if the verifier could redo the computation himself and make sure everything is done correctly, the verifier doesn't want to do this, okay? Because this is too costly or costs too much effort. So this is how we come to see SNARKs as a short proof of computational integrity. And this is maybe the most important application. And then there's another fundamental application, which is in the case there is also a private input to this computation, the SNARKs reveal nothing about these private inputs. So in summary, the situation that we have with SNARKs is something like this. There are two fundamental settings where they are useful. A setting that relates to privacy, where we have a computation that takes private inputs. For instance, you want to prove that you have the right to access a movie database. Well, you would need to show your ID to access this movie. You don't want to reveal your ID. So this is an example of a computation where we want to have a private input. And we would like, so SNARKs allow you to do this very efficiently. The other super famous case of application of a SNARKs, where it's a privacy setting, is anonymous financial transactions. Okay, by now it's probably well known that Bitcoin doesn't really give you any privacy. So Bitcoin is not anonymous, it's pseudonymous. So there are ways to de-anonymize transactions, and this is why there are cryptocurrencies offering a high level of privacy in transactions, for instance, zero cash. Okay, so this is a setting where privacy is fundamental. And there's also the other application, which is the scalability application. As I said, we don't really, not in all cases, there is a private input to the computation. Okay, in these cases, SNARKs are used for compress some data, or compress some computation, but still being able to claim things about computation, right? Usually when you have a data set and you really compress it and shrink it into smaller state, you lose the ability to prove anything about that. Okay, what SNARKs allow you is to have this compression and make it compatible with verification. So a typical example of this is our zero knowledge rollups. They are really not zero knowledge. This is why they are in this scalability setting. And these are come to see as one of the, are seen as one of the key technologies to scale blockchains, okay? The idea is that what they allow is, like, for instance, you have a bunch of transactions and all these can be compressed into some summary and some proof that all these transactions have been done correctly, okay? And this summary and this validity proof can be then stored on chain, but you're like really saving yourself so you don't have to store all the transactions so that you can later verify they have been done. Okay, so what I want to note here is that observe that when you compress, okay, when you have some information that's very large and you compress it a lot, you're destroying a lot of information. So in fact, when you have when you have already this compression, you almost have hiding for free. Okay, so when you have something that's very big, you compress it, there's almost no information that's left. That's why, in fact, the hard part of constructing SNARKs relates to make it compress and make it verify, and the hiding is somehow just kind of a bonus property that you get without a lot of effort. This is why in this talk, we will focus mostly on discussing this application, how can you compress and verify at the same time. So there's been a lot of effort on building zero knowledge proofs, and here's a, of course, non-exhaustive, like very, very summarized history. But of course, as you probably all know, like zero knowledge proofs are something very old in cryptography. We've had zero knowledge proof around for a long time. From the beginning, it was clear that you could prove anything with zero knowledge proofs. But the question was how to make this efficient for very large computation or for very large statements. Okay, we all know Sigma protocols. They allow you to prove something very small. Okay, now what's been happening since 2013 and so on is that people started finding ways to really prove with a SNARK very, very large computation. Okay, so this was like, it started like some breakthrough results around 2013, inspired on some previous work by Groth. the PCP theorem also has something to do and so on, but like here's maybe the starting of around 2013 and so on, the starting of practical zero knowledge proofs, okay? People were starting to think, how can we use this to have anonymous transactions for cryptocurrency, and all these applications that come later. So now we are sort of in what Eli Sasson calls the Cambrian explosion of zero knowledge proofs. So which means, as you know, the Cambrian is this era, the prehistoric area where there was an explosion of life. So we have an explosion of SNARK construction, many different types based on different primitives and so on. And also like some kind of zero knowledge industry, so that there's like a lot of companies that are putting an engineering effort behind all these cryptographic advancements and trying to build private blockchains and so on. So this was a brief summary of the history, and now I want to give you a basic sense of what kind of object is a SNARK and how you build it, okay? And usually there's like a common accepted terminology. There has been this effort, the standardization effort. So it's like a series of workshops that I'm called Zero Knowledge Proof.org. And there's like a bit of a common accepted terminology. It's like one of the few instances where people more or less agree, because otherwise you will see, usually it's like a dance of different acronyms and different definitions. But usually it's agreed to talk about a front end, which is how you process. You have a computation that you want to run, and the question is how you process this information into something that you can build later to build a SNARK, okay? And this front end starts, you want to run a computation, prove that it's correct, and what you first do is you represent it as you represent it in some ideal model, okay? So you say, and now I will think of my computation. So you idealize it and say, okay, my computation is like some kind of arithmetic circuit. So you write it in a specific, you have a specific representation, which means you have a specific set of instructions, of set of rules that you accept, okay? And then, so it can be arithmetic circuits, that's the most common thing. Maybe it's, you can make it arithmetic circuits with lookup, so you allow another operation, but you could also talk machine computations or whatever. And then from this, you derive a set of algebraic relations. So this translates into some relations between some vectors. And then you move to, and then you rewrite this algebraic relation as some kind of polynomial relations, okay? So I will talk more about this later. The important part here is that to note that this this is really not, you haven't done anything. All you have done is like rewrite a computation in a specific form, okay? So you started from some kind of program and you ended up with some polynomials that need to satisfy certain things if the computation is correct. Now there's the back end, which is what gets this computation represented in a certain way to a real SNARK, okay? And usually this backend, you still, the first thing you do is like, okay, you have a set of polynomial relations that you want to prove, and you write an interactive protocol that proves this polynomial relation, okay? So, and the polynomial, this interactive protocol consists of prover and verifier. They're sending each other polynomials, and they can make degree checks. The verifier can say, okay, please evaluate this polynomial at a random point, and so on, okay? But what you have to keep in mind is that this pre-processing polynomial interactive oracle proof is again an interactive, or it's again an idealization, okay? So again, this is really not something you want to have in practice. For one thing, note that this is not really something succinct. These polynomials have lots of coefficients. So it's just an abstraction that helps us to write our protocol correctly. Then the final step is where you really get a SNARK. And the idea is that in this polynomial IOP that we wrote, instead of sending polynomials, you will be really sending commitment to these polynomials. Okay, so you have replaced a polynomial, which is something that is you need a vector to represent a polynomial. No, you have to give all the coefficients. It's something that's not succinct. You have replaced it by something that is just maybe 1 point on an elliptic curve or something like this. Okay, and the main idea is that okay, and you also turn this protocol into non-interactive with Fiat-Shamir. And now the key point, what you really need here is a polynomial commitment, okay? So which means that when you commit to these polynomials, okay, you should be able to later, even though the polynomials are in committed form, the prover should be able to open these polynomials at specific random points. Why? Well, because the key idea is that and this is how we achieve succinctness, is that we are not really checking polynomials identities, but we are checking polynomials identities at random points. This is what gives us this succinctness property, okay? We have a super large polynomial. We want to prove, for instance, if these two polynomials are equal or something like this, but we don't check if they are equal, we check if the evaluation at a random point is equal. And what we need is to make sure that the way we commit polynomials allows the prover later to show that the evaluation at a certain point takes a certain value. Okay. The important thing to know is that here in this last step is where really we have like some cryptography. That's okay. So we have a compressing step. Here's where we get computational security. Everything else was just rewriting things and in a specific way. Okay, so this is how you build SNARKs, and what you think when you have to think when you are thinking, okay, how efficient is this? Is like we start by a large computation, and then we rewrite this computation in a restricted model where only certain operations are possible. Then of course this moves into a larger computation, right? Because it's not your native way of expressing the computation. And then it means that when you move to this algebraic relation, you will have super long vectors. And when you rewrite vectors as polynomials, you will have super high degree polynomials. And then at the end, since you will be committing to these very long polynomials with a polynomial commitment, for instance, maybe you have heard of the KGZ polynomial commitments in pairing friendly groups. The important thing is that this translates immediately into a lot of cryptographic operations for the proof. Okay, so this is why SNARKs are very expensive. Here you have an example that is like not really, is like a sort of made up example of like how would some kind of parameters would look like. Okay, so what are we talking about? What's the size of this computation? So let's say you want to prove a circuit of 2 to the 20 gates. That's not very big, might look big, but it's not. And then you have to do you will define the circuit over a field with 255 bits. Okay. The proof size that you will end up at the end of your SNARK maybe are 3 points on an elliptic curve. That is like a pairing friendly elliptic curve that has around 255 bits of order, and it's defined over a field of 376 bits. Okay, so then what does the prover need to do? Maybe he needs to do 7 fast Fourier transforms of size 2 to the 20 to multiply the polynomials, do some divisions, and so on. It needs to do multi-exponentiations in the group that are as the size of the circuit. So maybe it needs to do 4 to the 2 to the 20 exponentiations. And okay, so the prover is very expensive, but on the other hand, like these kind of parameters, which are inspired by, is more or less what you need to do for Groth 16, which is the most efficient SNARK, at least for the verifier. The verifier only needs to do 3 pairing operations, okay? So if you think about this, is like it's completely mind-blowing, right? Like there is a super large computation, and the prover, the verifier only needs to do 3 pairing operations to verify. It doesn't matter how big it is. Okay, so that's mind-blowing, but of course the price to pay is that the prover is doing a lot of effort. Okay, so okay, so the main point is that, as I said, scaling the prover is somehow the question in SNARKs, okay? So how do you keep this low verification cost, but you make the prover cheaper, no? Okay, there are approaches that I will not discuss so much, that what they do is like they, of course, like the kind of parameters I gave here are for SNARKs defined over discrete logarithm groups, where you need to have a discrete logarithm hard problem, so you need a large field, a large curve, and everything. There's an alternative approach based on codes that can use a smaller field. So in this sense, they can get a cheaper prover, but then the size of the proof, the verifier effort is much bigger. Okay, but this is a simplification. But let's say that it's the main problem in SNARKs is really to scale prover work. Okay, so I wanted to give you a sense of what are the main approaches that people are trying to follow now to scale prover computation. So one of the things that's people have been talking a lot in the last half year, in the last 1.5 years and so on, are lookups. So what are lookups? So lookups try to, the problems that lookups try to address is this problem, okay? So you have a large computation and you have to represent it, and there's a blow up here, okay? So the idea is like, if you make so the idea is that if you, inside the computation you want to prove, there are there is some specific subcomputation. For instance, you want to prove that something is the evaluation of a hash function, or that a certain element is in a certain range. The idea is that instead of proving it and writing a circuit that has a subcircuit that is trying to prove this, which can have quite a lot of gates, right? Because like, imagine that you want to prove that Y is the image of a certain element with a hash function. If you write this as a circuit, this will be very big, okay? So the idea is to replace this very big subcircuit with an operation that just looks up this value in a table, okay? Of course, the problem here is that you now need to design some polynomial IOP, so some way to encode these statements as some kind of relations among polynomials and so on. But the final goal and the effort in the last half a year or something has been, not half a year, in the last 1.5 years and so on, has been to try to make the prover that does these operations on the table very efficient, okay? In particular, what we don't want is that the prover that is proving that this value is in the table depends on the size of the table, okay? The dream would be that you can build like super huge tables, okay? So that you can express computations, like very large computations, as just one lookup, okay? But at the same time, this poses a problem for the prover if the computation has to depend on the size of the table, okay? And there's been a lot of progress that, like, there's a paper coming at Eurocrypt this year that's addressing this problem, and their claims that they are closer to what is called the lookup singularity, which is the lookup singularity is something that was proposed by Barry Whitehead, which is like a blocker, I don't know, who proposes to say, okay, suppose we can have a model of computation where we only do lookups. We don't have multiplication gates, we don't have addition gates, we just do lookups, with the goal of making this more efficiently verifiable. So like to make sure to make it less easy to make bugs in the code, okay? The idea is like, if you can build a table and simplify your program, then you seem very cool. Is it clear? Okay, so anyway, that would be the final goal, to have only lookups. For this, we would need huge tables, and then you have to find a way not to make the prover dependent. Okay, so this is one area. Then there's a lot of effort too in building SNARKs with linear provers, okay? So the idea is that these very efficient constructions like ROT16, they are not linear in the size of the circuit, but quasi-linear. So they are like, if the circuit is of size C, then the running time is order of C times log C. Why is that? Essentially, this is because there are Fourier transforms in fact here. Okay, and the Fourier transform is what they give you this log C thing. And that and Fourier transform, apart from this logarithmic factor, which can be quite a lot when you have like large computation. Apart from that, they are people in some, they are not very liked because they have, it's not easy to speed them up in some sense because they have like random memory accesses that are not very local. Like there's a bunch of reasons why people don't like Fourier transforms. They would prefer to do just multi-exponentiation. Okay, so essentially this line of work, what they're trying to do is eliminate Fourier transforms. Then there is another effort. I just put it because that's fresh from the oven. So I can see this is from February 6, 2024. There was recently the successful development of the world's first zero knowledge proof system on chip. Acceleration of chip. Okay, so there's been quite a lot of effort to accelerate to do hardware acceleration for zero knowledge proofs, and this is the first chip that was announced recently. Okay, so these are general trends, and something that and now I would come to other approaches that I relate more to what I have been doing. So there's another approach. The fourth approach would be, for instance, to do privacy preserving delegation of SNARK prover work. Okay, so the idea is computing this prover requires, doing the prover for a SNARK requires quite some effort. Now the idea is, okay, imagine you want to do this on your phone. What can you just distribute this among several people and let them do it for you? The problem here is that you want to do this in a privacy, even if you don't want to do it in a privacy preserving way, that's not really simple, but if you want to do it in a privacy preserving way, that gets more complicated, okay? You want to make sure that you can distribute your witness among some servers, okay? The servers are magicians, following, this tradition in zero knowledge proofs where powerful servers are wizards or magicians that can do a lot of computations, and the rest, the people with a normal phone, normal laptops, they are muggles or people that don't have high computational power. Okay, and the idea here is like you want to distribute your witness, and you want to make sure that even if some parties collude, they will learn nothing about your computation. And you also want to make sure that they are doing the SNARK proof correctly. Okay, so that if they somehow, there should be a cheap way for the muggle to check that the servers have computed the proof correctly, and the provers should learn nothing. Okay, and this has been the focus of some recent works in the last 2 years. Okay, and for instance, this paper at USNICS last year, EOs of CASA and other people, and some work on collaborative SNARKs from 2 years ago from Dan Bonnet, where he's like exploring a setting where people have different pieces of a witness and they want to jointly compute the SNARK proof. And the final goal is to make sure that with this sharing, that when you share the proof, you're able to prove larger instances than you would do locally. Okay. Finally, something that's been really, really the focus of a lot of research in the last, again, I'm talking about 1.5 years at most or something, like everything's moving really, really fast, are folding schemes, okay? Folding schemes, like there's like probably a lot of papers now on folding schemes, and everything started with a paper of Coppola, Setti, Inciala, or something like this is the NOVA. It's called a paper that's well known as NOVA. where they introduced this notion of a folding scheme. What is a folding scheme? A folding scheme is a way, so if you have an NP language and a relation, the idea is that a folding scheme consists of two algorithms, a fold algorithm and a verify algorithm, okay? Fold verify algorithm. So what folding essentially does is if you give me two instances of the language, I reduce it to a single instance. So, so the idea is that instead of, I want to prove two instances, I want to prove, oh, sorry, that's the type, which should be x2. You want to prove x1 and w1 and x2 and w2 are in a language. And what you do is like you create a randomized instance that in some sense is a linear combination of these two instances in such a way that knowledge soundness is preserved. So the idea is that you have collapsed these two instances into a single instance. And if you later prove that this single instance is in the language, now you also know that the two other instances were in the language, okay? What's cool about this, what's the nice thing about here is that when you create this combination that collapses the two instances into a single instance, that's quite fast to verify. Okay, that doesn't cost you a lot of effort to verify. And the prover, and also doesn't cost much to verify, and it's also cheap for the prover. So collapsing two instances into one is much cheaper for the prover than proving each of these instances separate. Okay, let me repeat. So the idea is instead of proving two different instances, you create a single randomized instance that's a combination of the two, and you prove it. Okay, now you need to prove that you have folded these two instances correctly so that you have really collapsed them into a single instance. And you also would need to prove eventually that the randomized instance is in the language. But the cost of this is in total cheaper than just proving that the two instances were in the language. Okay, so you're replacing proving two things by proving that these two things collapse into a single thing. Okay. So in some sense, what you have to think of folding as some way of delaying the proof. So you want to prove many things. You don't prove that they are satisfied. You keep collapsing them into a single instance. And at the end, you will do the really expensive part, which is really prove that your thing is in the language. Okay. What time is it? Okay. Okay. Good. Okay, so anyway, the point is that this is like, it's been a very important, there's like lots of papers on this, trying to use this idea in many cases, okay? So that's been like because the way you have to think of folding is some kind of prover amortization, okay? You're amortizing the cost of computing a SNARK, which is very expensive, and you just compute, and you end up only computing one single proof. Okay, so finally, I will talk about some results of some things I've been working on, again, very much on the high level. And I will continue on this idea of amortizing prover work, okay? The idea is like, if you cannot reduce the cost of the prover, try to amortize it. Okay, so try to prove many instances at the cost of one. The first thing I will introduce is a SNARK that's very simple and that I think has like some properties of being the minimal building block that you need in some applications. And then I will show how this applies to zero knowledge as a software as a service, so like delegating prover computation, and then an application to IVC, which is incrementally verifiable computation, which I will tell you in a second what it is. Okay, so what is Marlin? Again, let me, I know by now you're probably knocked out from so much information, but let's go back to the beginning. So how do we create a SNARK? Well, we start by, we have a circuit, no? We have represented some computation in some way that as a circuit. And then from this, we will write an algebraic relation. And I want to give you a sense of how this is done. So imagine our statement is we have a circuit and we want to prove that this circuit on public inputs 1, x1, the 1 is always there to take care of the constant, okay? But the circuit on public inputs x1 and x2 evaluates something public, which is x3, okay? There exists some secret information so that this circuit correctly evaluates to x3, okay? So in this case, what we're trying to prove is there exists some Z4 so that this circuit evaluates to x3, okay? And the way, and this is done by reducing, so what we do first is reducing this problem about circuit satisfiability to some set of linear relations, and this is called an R1CS constraint system, okay? So this is a very famous way to represent circuit satisfiability, okay? So it's just, this is the Hadamard product. So it means the pointwise product, okay? So you can see that you can write these matrices and then the result will be times the witness will be give you this vector and this, oh, because I'm covering half of the, okay. So you can see that the product of this vector with this vector will give you this vector. Okay, this is what it means, the Hadamard product. Okay. Anyway, the point is that the things I want to highlight here is that this rewrite, if you do this rewriting, first these matrices that describe the computation, they are public. They are part of how you describe the circuit that you want to do. Okay, you can derive them from the description of the circuit. And the other thing I want to highlight is that these matrices are more or less the size of the witness, right? Like the size of the witness, which is essentially the size of the circuit. Technically, they are the size of the input plus the number of multiplication gates. Anyway, the point is that when the computation is large, these are very large matrices. Okay, that there are matrices that the verifier, if the verifier is sublinear, the verifier cannot even read these matrices. Okay, so in summary, when we see the previous slide, we see that for proving this kind of circuit satisfiability relation, we need to prove three different things. Okay, we want to prove that some public inputs are correct, that there is a certain Hadamard product relation, and also that there are some linear relations that are satisfied. Okay, so if I know how to prove these three things, I know how to create a proof for a general computation. And again, there are some facts about matrices. They are public and they are also sparse. Okay, that's an important thing because otherwise that would be too much for the proof. Okay, so now that we have this computation represented as a set of algebraic relations, the question now is how do we turn this into polynomial relations? That's what we need to do for SNARKs. And I don't expect you to really follow this, but the point is that all we're doing is like when we have a vector, we can translate it into a polynomial. Okay, there's a direct way to encode a vector as a polynomial, and any of these relations, the public input relation, the Hadamard product relation, and an inner product relation, they automatically translate. This is like, here there's no cryptography, no interaction, nothing, okay? This is fully non-interactive. It's a way to rewrite statements. If this happens, then this will happen, okay? So there's some polynomial relations among some vectors, okay? Now I want to highlight one thing here, which is that as you can see in this list, this tells me how to prove certain things. It also tells me how to prove one inner product relation. But in reality, I need to prove many linear relations, okay? So this is not that I forgot to put it here, but it's actually, there is no really a known way to do this in a non-interactive way. There is no clear algebraic translation on how to prove many linear relations. We know how to prove one inner product, so one relation, but not many. So in reality, what people, and I think that's very important to understand, that the difficult part of SNARKs in some settings is like proving the linear relations, okay? So then because of this, there have been different approaches to address this problem with the linear relations, okay? The most famous, the most efficient proof system, which is GROT16, has its own way to deal with linear relations, which relates to these quasi-adaptive, non-interactive zero-knowledge proofs. But the important thing is that this way of dealing with nonlinear relations is not universal, which means that you need a different setup every time you change the constraints, which is like a no-go, because maybe you want to touch something in your circuit, then it means you need to run another ceremony to generate parameters and so on. And then there are two families of ways of proving this, by proving that you can do a permutation argument using some technique of Bayer and Groth that essentially encodes coordinates as a vector of some roots of some polynomials, and you prove these two polynomials are the same. And then there is another, which is the one I'm interested in. There is another way of doing this used in these proof systems, where like what you do is somehow the natural strategy. So you want to prove that y is equal to mz. So what you do is you pick some sufficiently random vector and you collapse, you do a randomize, you collapse all these linear relations into a single relation, okay? Now, what's the problem? So what is worth noting about this approach? Well, the problem here is that the point here is that everybody, the verifier himself, could be computing this RT times M, because the matrix is public, okay? So the verifier has the random coins, he has the matrix, he could compute this random matrix times M, okay? But that's not something that you want the verifier to do. Why? Because this would be too much effort for the verifier, because the number of rows in the matrix is proportional to the witness size. Okay, so this is why a significant part of the SNARKs that use this approach for proving linear constraints, what they do is they put significant effort into proving that this collapsing has been done correctly. Okay, although the verifier could do it himself, but you don't. If the verifier does it, then it's not a sublinear verifier. Okay. Okay, so this leads me to this observation. So if of these two known ways of proving linear relations, where for universal SNARKs, which means SNARKs that have a setup that's for every circuit, this Plum type of approach, which is based on a permutation argument, everything is a private computation, okay? Because when you're showing that these two polynomials are equal, you need to know the y's and the z, and this is the witness of your computation. Z is the witness of your computation. Whereas here, in this type of paper, Spartan and Marlin, this part of the computation is something correct. Like the prover does this, but it's not using any witness, okay? And then the other part is like this inner product with the witness, and this is private. Okay, so this leads us to propose this new proof system, which is based on the Marlin proof system, which is a universal SNARKs on pairing curves, on pairing friendly curves. And the point here is that if you look at the SNARK proof system, you can identify everything I told you, okay? You can see that this part is for proving a Hadamard product. You don't have to get it now, okay? But like the point is like you can understand that step by step, the proof system is doing exactly what I told you. And then there is like a certain kind of round here that involves quite some number operation that is really proving that this computation is correct. Okay, and this is something that the prover is doing to avoid the verifier some work, but in reality, the verifier could do it himself if he was willing to do some this computation. Okay, so this leads us to the SMARLIN proof system, where we just eliminate this round. Okay, which is in some sense is like a SNARK. You can think it in two ways. It's a SNARK with conditional verification, so with a SNARK that tells you that the proof is correct if you believe that this is true, like if you don't check this statement, but you believe it is true, or a SNARK where the verifier is linear. Okay, so it's a SNARK where this public computation can be done by the verifier itself. Okay, why am I interested in this proof system? Because it's like a sort of the minimal private computation that the prover is doing. Okay. Now, we're almost, so I will show you two quick applications of this, okay? And then we'll be done. So I think this is interesting for delegation of the private delegation of proving of SNARK provers. Why? Because privacy preserving delegation of a computation is something that is always expensive, right? Because you need to, in some sense, you need to create redundant data because you want to make sure that even if the magicians collude, they will not learn the witness. So in some sense, it's unavoidable that you're duplicating and you're creating more computation in total than you really need to do, okay? So my suggestion is that we should focus on doing privacy preserving delegation for this small proof system where it's a minimal thing that needs to be done locally or privately. And the public computation, like this third round of Marlin, can be delegated to a powerful cloud. It can be done by anyone, so we can put it by this, okay? So in some sense, there's been a lot of discussion of what is the right proof system that you should be using for private delegation of computation. I think it's this Marlin, because it's the minimal you need to do locally, okay? But then, okay, and then that's it. But there is something that concerns me still, is like if you're delegating the computation to a prover, and so this would be the server that is doing the public computation for everyone. So this server is doing a lot of work, right? Because it's getting a lot of statements from different people. No? So he has, like, in this case, he has to create 5 different proofs. And we want to have some amortization, okay? We would like, so of course, if you're in a setting where you want to delegate computation, you want to make sure it's as cheap as possible, okay? So then how could we, the question that we address next is, how can we make sure that this prover is not doing like one different proof for everyone, no? And then it can amortize the work that it's doing. Okay, and this was something that we proposed with my former PhD student, Alexandros Zakarakis. We proposed to talk about folding scheme with selective verification, okay, where we have a server and is getting statements from many different people, and we want to do something like folding. So we want to make sure that the verifier just has to compute one single proof, and this will be proving all the different statements, okay? So, and for this, what it's the same idea. So what the prover is doing is aggregating all these proofs into a single statement. Now, and then proving this single statement with a SNARK or whatever you want to use. And then the interesting thing is that the prover, the prover also do, it will give like cheap, these are like sort of like folding proof. It will show each of these proofs will make sure, will prove that the statement of model number 1 was included when computing the aggregated statement, okay? So there will be two parts. There will be a final proof of the aggregated statement, and then very cheap proofs that make sure that all the individual statements were taken into account when creating the big statement. Okay, is this clear? So this is what we want at the end. We want that the heavy part, which is the SNARK computation, is done once, and that on top of this, that there should be a way to do cheap individual proofs that each statement are included. The other important requirement, because it's like a natural requirement here, is that we want to make sure that the verifiers do not need to know or read the other people's data, right? Like when you are attending a service, you're not expected to know what all the statements that the server is proving, okay? And this is why we call selective verification, because you are only verifying your statement, the proof of the global SNARKs, but you are not required to read all the proofs of the individual matters, okay? And this is a big difference with aggregating proofs, right? When you're aggregating proofs, you are reading all the statements, and then you make sure the combined statement is true. Here you want to make sure you don't have to read all the statements, okay? The way we achieve this is by creating a tree of folded statements. So everybody submits their statements, you create a tree, and the root is the aggregated statement where you prove everything. And how do these folding proofs look like? Well, it's a sort of Merkle tree approach, okay? So you will be, when the verifier I wants to know that his statement has been included in the root statement, it will have like the sibling path. It can do the folding verification along the path, and it will make sure that it knows it's, that each statement has been included, okay? So in summary, our idea, we had this idea on selective verification in some context, and we realized that's like really good for applying it for the setting of public computation, okay? Because now we have that each, so we're thinking of the setting that the prover is doing, on one hand is that delegating to a set of servers the computation of the private part, and then it's delegating to a single server, or maybe he can do this locally, okay? Either it does it with a privacy preserving protocol that is expensive, or does it locally, and then it delegates the public computation to some server. And then we realize it's a perfect application for folding schemes, okay, with selective verification, to applying to amortize the cost of doing this public computation. Okay. So that's it, okay? So this is the takeaway from this application. I think I'm running short of time. No? No? Okay. Okay, so the point is that at the end, what we have achieved here is cheaper prover work, but without sacrificing the complexity of the verifier. Okay, improve aggregation, the verifier is linear. Here, it will be logarithmic in the number of statements that you want to aggregate. Okay, so the last application of this, which is also one excuse to tell you very briefly about recursive proof composition, which is, I mean, it's a topic that probably requires days, okay? So, but just give you the basic key ideas. I think that will be interesting. So not so much for the application that I will tell you about, but I think it's very interesting to learn about these developments, because that's a very, very active area also in SNARKs. So very quickly, what is recursive proof composition or incrementally verifiable computation? So incrementally verifiable computation and proof carrying data are two related concepts. And the idea is that we have a computation that is like sequential, okay? So it's like, in some sense, we want to do a SNARK proof of a certain computation, but this computation has a sequential nature. So it can easily be divided into different steps, okay? So the idea is, instead of proving in one single shot that some computation has been done correctly, you break down the computation of these proofs into smaller steps, okay, into T steps, where in each step you're more or less applying the same set of rules, okay? So why is this good for? Well, the idea is that instead, the prover no longer has to store the whole witness or do the whole proof in one shot, so it can save like memory, okay, because it can keep just the local information that he needs at each step of doing the proof, okay? Or also, it can also be useful in cases where you somehow you want to start computing the proof before you have all the statements that you want to prove, okay? Okay. So the setting is like this. So you have some prover, which depends on some function f, okay? And what you are trying to prove is that you have some function f, some initial state z0, and some final state, some final result of the computation that is zt, and you want to prove that somehow there exist values, intermediate values that are consistent with the fact that you did this computation correctly at every step, okay? So this is incrementally verifiable computation because you can see that it's, the idea is that it's incremental, right? Like every time you start by, you have some input of the computation, some witness, and then you have a witness that a proof that this computation was done correctly, and then you move to the next step. And the proof that you computed is augmented, so it's incremented with a new computation that you want to do, okay? So it's like some kind of incremental computation. And there's proof carrying data, which is like a similar concept, but where you don't have this line as a graph, but you have a direct acyclic graph, okay? So it's a more complex topology of the nodes that are doing the computation, but it's essentially the same thing, okay? As far as I know, when this was proposed, the idea here was that this was what is called a hearsay argument. So what does it mean? It means that in each step, you hear that the previous proof was correct. So like you don't know the witness. So all you have is a proof that the previous computation was correct. And what you do is you continue this chain, right? Like you hear that the proof was correct, and then you continue and you keep proving, okay? So the important thing is that as they usually were defined, there was not really a private information that was transferred from one step of the computation to the other, but it was that anybody could continue this chain of computation, okay? Now maybe this concept is used a bit more loosely, so there's also, it's also accepted that there is some kind of state that can be private information that is transmitted from one step of the computation to the other. Okay, so this has been, this has a lot of uses to scale zero knowledge proofs. There's a lot of constructions on how to do recursive proof composition. And I want to divide this to you into 3 different approaches, okay? That's the current state of the art. So the first approach, which is the traditional one, was to do what is called full recursion, which is the setting that I described originally, okay? So these boxes in which, and that we create on each step, what they are doing is in each of these boxes, the prover, there's a prover that is proving that the computation is done correctly. And it is also proving that the previous proof would be accepted by the verifier circuit. Okay, so you're creating a proof that the computation is done correctly and the previous proof was also correct. Okay? And this was a traditional setting. Okay, and this is, so what this means in reality is that you have to create a proof for the circuit that corresponds to the functions and the verifier and the SNARK verifier. Okay, so essentially the prover has to run in time that is proportional to the size of the computation and to how big is the circuit of the verifier. So, and this poses all kinds of problems because it means you have to write the verifier as a circuit that you can do a proof about. Okay, so it means that you have, if the verifier is using hash functions, you need to write these hash functions inside the circuit and do things like that. Okay, but the important thing is that this classic or full recursion is really, again, a hearsay argument. Everybody can continue the computation because it's just a proof that you know a proof and so on. Okay. Then there is another approach that was very important that was proposed in 19, which was solving an important problem, which is that this approach, for this approach to work, you really need to make sure that the verifier is small. Okay, it cannot be linear in the computation because otherwise you need to absorb this circuit inside the verifier circuit inside the computation and so on. So one idea that, and the problem is that if you look at SNARK construction in the discrete logarithm setting, they need to do some linear computation. Okay, so the verifier is not short, and you couldn't do recursive proof composition. Okay, so and the main idea, a very important idea that came here was the idea, some kind of idea that's similar to folding. The idea is like, okay, the verifier is linear, the verifier is very big, I cannot fit it inside the circuit. What I will do is I will split the verifier into one part that is succinct, that I can put inside the circuit and prove in the next step, and one part that is not succinct, and what I will do for this part is some kind of folding. So I don't prove it, I keep it for later. That's the idea. Okay, so you're really not doing the proof, you're not really putting this, so you're not really doing this check that the verifier needs to do, that would be too big, but you keep the check for later. That's a bit of the idea. Finally, there's like the final approach is this split accumulation or folding. In fact, when I told you about folding, folding appeared exactly in this context. Okay, the idea was the prover does not compute any proof. Okay, it just keeps doing a commitment to each part of the witness of the computation. It keeps accumulating the witness, but it's not proving anything until the very end. Okay, so it's this idea of I'm delaying the proof and not proving anything. And all I'm proving at each of the steps is that I'm folding the instance correctly. Okay, I'm not proving, I'm just collapsing instances one on top of the other. Okay, what's the goal? The goal here is to make sure that you amortize the cost of the proof. Okay, so you only will do one last proof of the SNARK at the end, and in the meantime, you just keep accumulating. Okay, so this is mostly these are the three approaches that there are. This is a slide that I adapted from Kotapalli, Sethi, and Sethi, which is at SNOVA, and this is the state of the art of folding of recursive proof composition. You have one of these three approaches. The important thing to know is that we have this setting. No, we have, on one hand, if we look at the first two approaches, we have that the prover is not really saving anything. Okay, it's a hearsay argument, so anybody can compute the chain, but the prover is not doing less effort than it would take to compute each of the proofs individually. On the other hand, this folding scheme, this is why there's so much interest and so much people are like them so much, is because at each step of the computation, you're really almost doing no effort. So you're not doing this effort of proving at each step. Okay. The problem with these folding schemes is that you need to transfer not only the proof, but you also need to keep transferring the witness, right? Like, since you are not proving anything, you're only computing the proof at the last step. You need to make sure that at the last step, whoever is doing the last step has the full witness. Okay, so it's not something that anybody can continue because there's a certain state that you need to pass to the next proof. Okay, so that's it. So all I want to draw your attention to is that if we look at this Marlin proof system, where we thought of it's a proof system where we are splitting computation into a private and a public part, we can get something that gives you a new trade-off in the space of proof systems, okay? Why? Because the idea is that we can, the main idea is do a recursive proof composition where at each step you only prove the private computation, okay? So, and you don't really do this check that would be linear, that refers to public computation. So what do we gain here? We get something that's new, which is the trade-off where we are still gaining on prover computation because you're not doing the full proof. But on the other hand, you still have this feature that anybody can continue the computation because it's public computation, so everybody could do it, okay? Okay, that's a very complicated topic, but I hope this, at least to me, it's useful to summarize the state in this R of this. Okay, so you could do this. This explains that how you would delegate, so how you would implement this idea with this Marlin proof system, Mar-Lin proof system. Okay, so that's it. Okay, so the takeaway of these last results that I gave you is that I think that focusing on this private and public computation, I think leads to meaningful saving and insights and new trade-off in the design space. I think this Mar-Lin should be the standard when the proof is delegated, okay? Because it really minimizes the part that needs to be done locally or through privacy preserving techniques. The interesting thing that I didn't really put a lot of emphasis on is that if you really look at the private computation, is also cheaper than in some, because it only depends on the size of the witness, and the public computation depends on the number of additive gates, the sparsity of the matrix, and so on. The point is that there is a certain asymptotic gain also of removing this public part. So I think that's a very meaningful way to look at things. Okay, so this was to give you a sample of things I've been thinking about. And finally, I need to finish this with some conclusions of what I think is like the trends. And I think I hope I convince you after this talk that there are many different constructions of SNARKs based on different primitives, and that there's a large design space, so that many different trade-offs are possible. And there are promising venues for scaling them. I still think that we are, like, my takeaway is that we are still deep in the Cambrian era, no? That we're still like in this era where there's like new things coming, and that maybe shake, so that maybe change the landscape quite a lot. So I think there are still things to come that will probably affect how we think of SNARKs construction. The important thing is that there's so much funding, and there's really a massive engineering effort behind all these SNARKs. So this is what's pushing the state of the art so fast. And, you know, as I was giving this talk to some, a similar talk to some other people, and I mentioned the Cambrian explosion, somebody told me, you know, but the Cambrian explosion ended up with a massive extinction, which was like quite, it was not, I was like, okay, that doesn't look too promising. So I hope really that this doesn't end up with a massive extinction. But maybe a bit of extinction wouldn't be too bad, like in the sense that I think that the dust needs to settle a bit, and there has to be a bit of more clarity and convergence of all these different constructions into a few ones that are used for different trade-offs. And that's it. So I'm happy to take any questions.